Okay, so this class is all kind of about class prediction. Just make sure you read the notes. In the notes, I kind of start off by giving some motivating examples for how, for example, in marketing, we'll use it for promotion prediction, churn prediction, or choice prediction, where a consumer has a set of products, for example, 3 different brands of coffee, and then they will make a choice as to which brand they prefer. In IT, it can be used for fault analysis. It can be used for image recognition purposes, for security, for disease prediction. And in accounting and finance, it's used a lot for fraud prediction, fraud prevention prediction, and going concern and bankruptcy prediction. So let's just actually start off with a very simple problem. And this is the one from the notes. So we have y. This is the dependent variable, and it is does the customer churn. I.e., if they churn, they don't renew their contract. And that's going to be kind of no or yes, where no is a 0 and yes we can actually have as a 1. And that's, as in regression, that's going to be the dependent variable. Let's just get a little bit of notation. And if we were trying to predict this, we would have y hat. So we're trying to predict a customer churns, we make a prediction, that's going to be my y hat. So we have the independent variables, which we're using to make the prediction. And we're going to have maybe something like how long has been a customer, so number of years customer. Kind of the annual, the price of the plan. Maybe some sort of customer satisfaction score. The number of hours they've spent on customer, they've called, so hours of calls in customer service. Or if this is a cell phone plan, just how long we actually have, they've spent on the service, and the number of texts they've sent. So these are kind of just, depending on our scenario, we've got some sort of usage characteristics. And I guess X6, if we're going with the cell phone plan, that's going to be the data used, or something like that. So we're trying to predict whether our consumers are going to renew or not based on this information. Okay, so let's actually put this in a slightly different way. We have my x's, and each of these guys, to 6, these are going to be features. So we can use M, we can use K. Let's use M as I used it in the notes. So we have M different features. In this case, this would be 6. And then we would have a Y1. Now, we denote a certain amount of data as training data. This is the data that we're going to build the model on. So this will go all the way up to X N1, 1. So we have N1 training items. And then we have y all the way up to n1. So, I mean, this seems a little bit complicated, but we have a data set of 1,000 items. We take the first 500, n1 is 500 as training, and then we take 500 as test. n2 is 500. And then we kind of we start off with our test data, so root line n1 plus 1. And this will go all the way to x n1 plus n2, with the training of the test data. Let me just scroll down a little bit. This x plus n2, comma m. And then we've got, this will be y n1 plus 1, all the way to y n1 plus n2. And again, this is my n2 test items. So what we're going to do, well, let's just draw a line, is we're going to build our model up here. This was something sometimes called the holdout sample or the test sample. And then we pretend we don't know these guys. So we pretend we've got no idea what's going on here. And we use our model, we use this data, the independent data, and our model that we have from before in order to make these predictions. So we've made all these predictions, and then we need to calculate the predictions. Now, you know, these are going to be zeros or ones, so we might have something like that's a 0, 0, 0. So we'd go through and we'd say, okay, we got that wrong, we got that wrong, we got that right, we got that right, we got that wrong, we got that right. So here we got basically 50% right, and we got 50% wrong. So that's our measure of success. So let's just actually put that a little bit more formally. We can define an error, which we're going to call the mean error. We're just going to call it the mean absolute error. And this is, you know, we're going to average across our n2 test items. And for each of the test items, so this iterator is just saying we're going through each of the test items. We're just going to give it a 1. This notation's a little bit mathy, but it's just give it a 1 if our y's are not equal to the prediction. So we predict a 0 and we get a 1. We basically add 1 to it. We could give it a 1. And this is just what we call an indicator function. And we just literally add up all the times we were correct. And we divide it by the number of test items. So this is just proportion wrong. But we could also have the accuracy. So let's get it clear. Error is we get it wrong, and accuracy we actually get it right. Again, we have our beautiful indicator function here. And this is going to be, we get it right, and this is the proportion correct. Okay, so we're now going to go on, and I'm just going to kind of make this a little bit more detail and talk about some of the things we had in the discussion today, you know, where we look at things like the problem of false positives and true negatives. So we're just going to do this in a little bit more detail. Okay, so let's go through the example in the notes, and I'll just kind of give a little bit of extra explanation or not. So we're trying to predict bankruptcy. And we're going to have, you know, yi equals 1 is a company becomes bankrupt. And yi equals 0 is not bankrupt. So we have a lot of training data, we build a model, then we have some test data and we make predictions on the test data. So y hat I equals 1, we go predicted bankrupt, and y hat I equals 0 is we predict not bankrupt. These are just my predictions. Okay, so I'm going to test my ability to draw a table. So what we're going to do is we're going to have the actual values across here and the predictions in the rows. Okay, I give myself 9 out of 10 for that table. That's better than I usually do. So this is yi equals 0. So the true label is 0 and yi equals 1. And these are our predictions. So this is what we call a kind of a classification table, but this is just going back to our chi-squared tests. This is actually a contingency table. And so let's just say we do the bankruptcy, and most are not bankrupt. So we have yi equals 0. So these are the non-bankrupt ones. And we have 95. And then we have the ones that are not bankrupt, we predict bankrupt 11. Then we have bankrupt, but we predict, so we're wrong here, not bankrupt is 8. And conversely, we have they're actually bankrupt and we predict bankrupt, then these are 18. So what I'm going to do, I'm just actually going to move that 95. So let's actually define these guys. This is my true negative. It's not bankrupt and we've predicted it correctly. This one is not bankrupt, but we've actually predicted it is bankrupt. This is going to be my false positive. And then is bankrupt, and we predicted bankrupt. So, yep, we've got it right. This is a true positive. And this is it was bankrupt, but we got it wrong. This is the false negative. Okay, and what I'm going to do is I'm going to just do cutouts of this table, and then I'm going to actually calculate a range of metrics for evaluating class. Okay, so let's just make a copy of this table. Let's make it as big as the previous one. Perfect. Okay, so let's just think a little bit about the level of accuracy. So let's just kind of use red. If we actually are here, then the true negatives and the true positives are actually what we're looking for. So let's just see if we can outline in red. Okay, that didn't work. Okay, so we have our true negatives and our true positives. So these are all the ones we got correct. And these guys are the ones that we didn't get correct. So actually we want basically the diagonals out of everything. So we can actually say that the accuracy equals the true negative plus the true positive, the diagonals, all over basically everything. So in this case, it's going to be 95 plus 18 all over 95 plus 8 plus 18 plus 11. So that's going to be 0.856. And that's going to be our measure of overall. So next, we're going to have what we call recall. Now, basically what recall is, it's going to be the number of true positives, what we get correct. So this is actually the precision. So the precision is the true positives over the true positives plus the false positives. So the idea is this: if we get a true result, what's the chance, of it actually being true? And, examples of this is if, for example, you're testing for a rare disease such as HIV, even if you have a low false positive rate, if most people are negative, your false positives are probably quite high relative to your true positives. So the idea is the precision will tell I get a positive result, so somebody's just been diagnosed with HIV. How likely is the case that they're just going to be diagnosed? So we have precision is going to be the true positives divided by the true positives plus the false positives, which in this case is just 18 over 18 plus 11 equals 0.621. And in fact, I think I was asked in class, these situations like rare things like bankruptcy, this precision is a good value because this tends to be a lot lower than the accuracy, because if I have a really rare event and it's hard to predict it, I'm liable to get quite a lot of false positives relative to the total number of true positives. So that is the precision. Okay, and now we actually get to recall. So this is, we have our bankrupt company, and what I want to know is what's the chance of me actually classifying it correctly. So we have the true positives divided by the true positives and the false negatives. So this is, we actually have, the company is actually bankrupt. What's the chance that I predict that it's going to be bankrupt? It's true positives divided by true positives plus false negatives. So the recall is going to be the true positives all over the true positives plus the false negatives. So in this case, it's going to go, again, this is going to be a little bit lower than the actual accuracy. It's very hard if most of your companies are not bankrupt to find the bankrupt companies. Which kind of brings me to the third one, which is specificity. Okay, so specificity is if we have an actual negative, what's the chance that we get this correct? So this is a very important metric if there's quite a high degree of harm that comes from having a false positive. So again, this is the chance in our bankruptcy example. If we're not going to be bankrupt, what's the chance of we actually getting this correct? So think back to the example I talked about in the discussions of where there was a computer system that was actually predicting whether or not you would reoffend. And if it was predicting you would reoffend, it was giving you longer prison sentences. So that means that if you have a false positive, that's probably bad for the person who has the false positive. So in that case, the specificity, would actually be a very important metric. And in this case, it's like true negative, and then divided by the true negatives plus false positive. But conversely, if we're desperate to find something like a bankrupt company, but that's very rare, my algorithm could just basically predict 0 all the time and get perfect specificity. But in that case, the recall actually would be much more important. So it's a trade-off, really, depending on your problem and your problem domain.